Grafting a pointed fighter jet nose onto a giant commercial airliner looks completely absurd, but it is the smartest military testing decision made in 30 years. Most people look at the Excalibur flight test aircraft and see a bizarre Frankenstein monster. They think defense contractors lost their minds. They are dead wrong. Pure strategic brilliance. This heavily modified Boeing 757-200 is BAE Systems' secret weapon for the Global Combat Air Program. How do you test radar so advanced at seas through modern jammer networks without risking a multi-billion-dollar stealth prototype? You do not put it in a tiny fighter cockpit. You drop it into a flying laboratory with 20 engineers sitting behind computers at 30,000 feet. You do not win modern air wars with faster airframes. You win them with clear electronic vision. That is the core premise. If you want a functional 6th-generation stealth fighter in active service by 2035, you cannot build it using 20th century habits. The old way of flight testing military hardware is completely broken, and defense budgets can no longer absorb the damage. Look at the nightmare that plagued earlier stealth fighter rollouts over the past 2 decades. Testing advanced radar inside a single-seat stealth fighter is a major disaster for scheduled timelines. Think about that for a second. Why throw a single test pilot into a crowded cockpit to debug millions of lines of complex code while pulling 5 Gs? Modern stealth fighters run on over 20 million lines of software code. The pilot is busy flying the plane and managing flight controls. They cannot look at diagnostic telemetry, tweak software scripts, or monitor heat distribution across thousands of individual radar transmitter modules. If a software bug crashes the main sensor grid at high altitude, the pilot flies back to base with 0 actionable diagnostic answers. The flight hour is completely wasted. $50,000 burnt to ash in 60 minutes. Multiply that by hundreds of test flights, and your fighter program runs 5 years late and tens of billions over budget. It happens every single time. Military aviation keeps repeating this exact mistake because tradition demands testing fighter electronics inside actual fighter airframes. That logic fails miserably under modern software demands. If you want to understand how modern military technology actually gets built behind closed doors, subscribe to this channel right now. You will start noticing how many key engineering decisions happen right under your nose. BAE Systems chose to break away from that broken tradition entirely. They acquired a commercial Boeing 757-200 passenger airliner, gutted the interior, and named it the Excalibur Flying Lab. They partnered with aerospace flight modification specialists at 2XL Aviation to execute the engineering work. Why pick a civilian airliner for a 6th-generation air dominance project? Spatial volume and steady stability. A Boeing 757 gives you a large, pressurized tube where flight test engineers can stand up, walk around, and operate full-sized engineering workstations. It offers wide internal space for heavy computing racks, liquid cooling pumps, power conversion units, and signal analysis gear. But even more importantly, a commercial jetliner stays airborne for 5 to 6 hours straight without needing mid-air refueling every 90 minutes. It provides a steady, predictable flight envelope. Instead of flying a high-risk, unproven stealth prototype, you fly a bulletproof commercial airframe that operates reliably day after day. It transforms chaotic flight testing into a controlled, repeatable airborne lab experiment. The physical transformation of this Boeing 757 is radical. What happens when you chop off the nose of a commercial airliner and weld a pointed fighter nose directly onto the front frame? You ruin every standard aerodynamic profile on the aircraft. Engineers had to redesign the entire forward fuselage structure to support the physical weight and geometry of the future Tempest fighter nose section. They installed internal titanium support beams and custom wiring conduits running down the length of the lower passenger cabin. The forward radome houses the actual active electronically scanned array radar intended for the operational 6th-generation jet, far beyond a simple cosmetic fiberglass shell. Sticking a sharp, pointed cone onto a blunt subsonic airliner creates wild, turbulent air patterns right in front of the flight deck. Engineering teams spent months running wind tunnel simulations and stress calculations to ensure this nose modification would not destabilize the plane, disrupt air intake flow, or create dangerous wing vibrations during high-altitude maneuvers. Power requirements for next-generation military radar arrays are extremely high. Modern active electronically scanned arrays using advanced gallium nitride transmitter modules do more than passively scan the sky. They transmit dense electronic attack signals and process huge data streams simultaneously. That demands heavy electrical current. How do you feed a heavy radar array that consumes more electricity than a suburban neighborhood? A standard fighter jet alternator melts instantly under that kind of demand. You cannot fit extra electrical generators inside a tiny stealth fighter airframe without ruining its weight distribution and burning through fuel in minutes. The Boeing 757 solves this problem instantly. Its commercial turbofan engines generate huge reserves of extra electrical power. Engineers tap directly into those engines to supply steady electricity to the radar banks. They also built heavy-duty liquid cooling systems inside the cabin using specialized polyalpha-olefin coolant loops to dump excess thermal energy. Without constant liquid cooling, high-power radar modules fry themselves in seconds. Step inside the Excalibur cabin today, and you will not find rows of cheap passenger seats or overhead luggage compartments. You find large server racks bolted straight into the titanium floorboards. High-speed gigabit fiber optic cables run along the cabin walls, linking sensor equipment directly to analysis stations, signal analyzers, and engineering consoles. 20 specialized flight test engineers wear noise-canceling headsets and sit behind custom workstations during every single flight run. When the forward radar sweeps an airborne target 50 miles away, the raw signal data hits those consoles in real time. If the target tracking algorithm drops a signal during a sharp bank turn, an engineer sitting at workstation 4 edits the software code right then and there. They do not wait to land. They patch the software while cruising at 35,000 feet and retest the software fix 10 seconds later. Pure efficiency. That single operational shift speeds up software calibration by 10 times compared to traditional single-seat flight trials. The strategic stakes behind this project are immense. The Global Combat Air Program brings together the United Kingdom, Japan, and Italy in a joint defense effort to field a world-class 6th-generation fighter by 2035. That deployment date is completely non-negotiable. Prime contractors like BAE Systems, Leonardo UK, Rolls-Royce, and Mitsubishi Heavy Industries are pooling their industrial capabilities to deliver the jet on schedule. Peer competitors across the globe are building their own next-generation stealth platforms at breakneck speed. If the GCCAP coalition misses its 2035 deployment window, Western and Allied airspace dominance vanishes overnight. Air supremacy demands total radar visibility before an enemy air defense system even knows you exist. Developing a physical stealth jet frame takes time, but developing and refining the underlying electronic brains takes even longer. By using the Excalibur Flying Lab to perfect the radar grid right now, the engineering team ensures that when the final fighter airframe rolls off the assembly line, its electronic eyes are fully mature, bug-free, and lethal. What makes this 6th-generation radar array so exceptionally capable compared to older systems? It serves as a multifunction electronic warfare suite rather than a basic airborne radio sensor. Traditional fighter radar shoots radio pulses out, waits for those pulses to bounce off a metal target, and draws a simple dot on a display screen. That is basic 20th century technology. The radar grid mounted inside Excalibur operates as a radar, a passive radio receiver, an electronic attack weapon, and a high-bandwidth directional communications node. It uses digital beamforming to generate hundreds of independent radar beams simultaneously. It can detect stealth targets with microscopic radar cross-sections from vast distances. Simultaneously, it can project narrow, high-power beams of radio frequency energy to fry the guidance electronics of incoming air-to-air missiles. It collects terabytes of electromagnetic data every minute, sorting through dense background chatter to isolate threat signatures instantly. If this breakdown is giving you a fresh perspective on defense technology, take a second to hit the like button. It helps the algorithm show this video to more people who want real technical substance instead of superficial defense hype. Modern battlefields are choked with aggressive electronic warfare equipment and signal noise. Peer adversaries deploy radar distractors, broadcast high-power noise across military radio bands, and attempt to blind airborne battle management sensors. Can a combat jet survive when its own radar signature gives away its position to enemy air defense nodes? Not if its radar uses predictable signal patterns. The radar grid being refined aboard Excalibur relies on low probability of intercept waveforms. It scatters its radio pulses across thousands of rapidly changing frequencies every single second. This makes its radar emissions sound like meaningless background atmospheric noise to enemy direction-finding gear. Testing these complex frequency-hopping algorithms requires flying directly into dense electronic jamming environments over maritime test ranges. Excalibur captures the jammed signal data, calculates how well the radar filters out noise, and updates algorithm parameters immediately. Radar hardware means nothing if the pilot gets overwhelmed by raw information overload. That is where artificial intelligence and sensor fusion enter the equation. 6th-generation air platforms rely on intelligent algorithms to process incoming multispectral sensor feeds automatically. The radar feed inside Excalibur merges continuously with thermal optical cameras, electronic support measures, and real-time data links from naval ships, ground command stations, and uncrewed loyal wingman drones. The onboard software takes those thousands of messy data points and translates them into a clear, simple tactical picture. It identifies target airframes, ranks threat levels by urgency, and recommends optimal weapon solutions. The Excalibur flight engineers spend hours testing these artificial intelligence threat scoring models under real flight conditions. They simulate incoming mass drone swarms to verify that the target tracking software does not freeze or drop target locks under extreme operational strain. Let us look at the pure financial math behind this flying laboratory project. Flying a high-performance stealth fighter prototype costs upwards of $40,000 per flight hour. Every single flight hour wears out specialized radar-absorbent surface coatings, burns large amounts of fuel, and strains strict airframe life limits. If that stealth prototype flies for 2 hours just to evaluate a minor radar patch, you spend $80,000 for minimal diagnostic output. The Boeing 757 costs far less per flight hour to operate, and it collects 50 times more flight test data per flight due to its extensive onboard server infrastructure. Pure math. You get better data, faster answers, and dramatically lower overall development expenses. This bizarre commercial airliner is not an ugly side project. It is the single reason 6th-generation air dominance will actually work without breaking defense budgets. This strategy of using a commercial airframe as a fighter avionics testbed is grounded in historical precedent. Decades ago, Boeing modified a commercial 757 airliner nicknamed the Catfish to test the radar and sensor avionics for the F-22 Raptor program. Lockheed Martin similarly used a modified Boeing 737 called the CATBird to test the F-35 Lightning II sensor suite. Those American testbeds carried custom fighter, nose cones, and simulated wing sensor housings mounted right above the flight deck. They identified hundreds of software bugs and signal processing glitches in stealth sensor suites long before production fighters ever left the ground. The Excalibur program takes that exact playbook and upgrades it for the modern digital era. BAE Systems recognized that cutting corners on avionics testbeds leads straight to catastrophic program delays and budget overruns down the line. Zero excuses. They are executing this test strategy with total rigor and zero compromises. Mounting a radical, sharp fighter nose onto a Boeing 757 creates serious structural engineering challenges that cannot be ignored. The airflow around the forward airframe changes dramatically, creating localized pressure drops and turbulent air vortices along the lower forward skin. Engineering teams had to install specialized stress gauges and structural strain sensors across the metal skin near the modification joint. During test flights, technicians closely monitor structural strain readings to verify that aerodynamic loads stay well within safe limits. Pitot tubes and air data sensors near the cockpit had to be recalibrated to account for distorted airflow caused by the altered nose profile. If the modified nose causes excessive airframe vibration, it can introduce mechanical noise into the ultra-sensitive radar receivers mounted right behind the nose dome. Eliminating mechanical vibration is key. Even tiny microvibrations distort high-frequency radar beams, creating ghost targets on engineering screens. Pure precision mechanical engineering keeps the platform acoustically stable and airworthy. Defense contractors spend hundreds of millions building hyper-realistic ground simulators, but ground laboratories can never fully replace physical atmosphere. Ground testing cannot replicate high-altitude temperature drops, engine electromagnetic interference, atmospheric ionization, or reflections off ocean waves. You can run a computer simulation for 10,000 hours and convince yourself that your radar software is flawless. Then you take it up to 30,000 feet, and ambient static electricity creates false target tracks across the cockpit displays. Excalibur bridges that critical gap between virtual simulation and physical flight reality. It allows engineers to take digital twin software models created on supercomputers and subject them to real-world flight friction, extreme cold, and physical motion. Hardware builds the airframe, but software wins the sky. Bridging software and hardware in real air conditions is where victory lies. The flight testing roadmap for Excalibur is aggressively planned out over the coming years, leading toward operational integration. Initial flight phases focus on basic radar beam calibration, power management stability, and mechanical antenna steering dynamics. Once the basic hardware performance is certified in flight, the flight test schedule shifts toward advanced combat software integration. Engineering teams will load full tactical combat algorithms into the onboard server racks. They will conduct simulated aerial engagements against real target aircraft over isolated ocean ranges, testing long-range tracking, multi-target lock-on, and stealth detection limits under realistic combat geometries. By the time the actual physical GSCAP stealth fighter prototype performs its maiden flight, its radar grid will have accumulated thousands of operational flight hours aboard Excalibur. Zero guesswork. Zero day one software surprises. We are witnessing a fundamental shift in how military air superiority is won. In the 20th century, air victory belonged to the aircraft that could fly the fastest, turn the tightest, and climb the highest. Today, those physical performance metrics matter far less than computational power, radar range, and sensor fusion speed. A stealth jet that cannot process battlefield data faster than its opponent is just an expensive target waiting to be shot down. The Excalibur Flying Laboratory represents the modern reality of defense acquisition. It proves that raw computing power, signal processing efficiency, and airborne software refinement are the true metrics of modern military power. When the final fighter takes to the sky, its radar won't be a prototype. It will be a combat-proven killer. Game over. Why risk catastrophic delays when you can solve the hardest electronic engineering problems before the real jet ever leaves the hangar? That is why Excalibur exists. It is building the future of air dominance in silence, high above the clouds. If any of this technical reality hit home for you, like and subscribe right now. There is so much more military technology to uncover, and you do not want to miss what comes.